Hello everyone, I'm Paolo Marzioli
And I'm Lorenzo Frezza.
from Sapienza University of Rome. This video tutorial is linked to lecture 8 of the course, Receiving Data from a Dummy Transmitter, Part 2. In this lecture we will start from the end of lecture 7, where we successfully managed to demodulate the dummy transmitter data, and we will arrive up to interpreting all the data that is received by the dummy transmitter, simulating the telemetry from a space system or a satellite. I immediately hand over to Lorenzo, that will show you through his screen what to do to complete the lecture.
Hello everyone, welcome back to the lecture about receiving data from a dummy transmitter using an RSP and GNU Radio. We left last lecture with a script that was able to demodulate data and setting the signal to be between -1 and 1. Now we want to extract the bits from this signal. What we need is some sort of synchronization. We need to be able to synchronize the clock of the signal with a clock that is able to extract the bits from the signal. There are several available with GNU Radio. We will use the polyphase clock sync. As you can see, is in the synchronizer group. The polyphase clock sync takes a signal which is usually in a square waveform, and it will output a signal with only the content of the bits. The main two parameters are the samples per symbol, which is the ratio between the sample rate and the symbol rate, which is the baud rate. So let's write it. Sample rate divided by DEC divided by baud, because we need to remember that the sample rate coming into the block will be the sample rate of this chain, which is sample rate of the radio divided by 50, which is the decimation. The loop bandwidth, it's actually usually set to 2 times pi, so let's write an approximate value, divided by 100. You see that samples per symbol is still wrong. It's highlighted in red. This is because it's actually called sample rate, not sample rate. Let's correct that. Okay. Another thing that is missing is the taps. This is a required value, and it tells the polyphase clock sync what filter to use to synchronize the clock. To define the taps value, we need to define first a variable, which we will call RRC filter, due to the nature of this filter, which is a root raised cosine filter. So that's a root raised cosine filter. We will not go into detail on the meaning of this filter, because it is too advanced for the class, but you can type in this value, and if you're curious you can look a little bit more into detail on what a root raised cosine filter is. We'll need to define a variable called samples per symbol, which is actually the same value that we set in the polyphase clock sync, but we'll need to round it to an integer value. To do this, we'll do round sample rate divided by DEC divided by baud rate, and we'll set the samples per symbol to samples per symbol, so it's easier to keep track of. And you see that it will round to 33. So let's switch the type to float and put it in between the signal and the output. We forgot to include the RRC filter in the taps, so let's open the property of the polyphase and include RRC filter, which is our variable in the taps. Let's press play. And here we have the data. Now, you see that it is not longer a pretty square wave, but if we zoom in, we see that it is not a square wave like before. This is because this is actually the bits themselves, which go from between -1 and 1. You can actually see when this part is present in the signal, this is the transmitter switching rapidly between -1 and 1, so transmitting the bits 0 and 1, one after the other, for the preamble, which we talked about before. And you can see that the preamble, each bit is actually 1 bit long, which is what we wanted. We wanted a signal where each bit is a sample, and we only need to map the 1 value to 1 and the -1 value to 0. Then we have our bit sequence. To do this mapping, we can use a block called the binaries slicer. The binary slicer takes an input which is float, and it will output a signal which is an integer 8 or a byte. We can actually see in the documentation that it will slice float binary symbol, producing 1 bit output. And this is done specifically to use with polyphase clock sinks or other synchronizers. Let's then remove the time sync, which we don't need anymore. And now we want to do something with this output. We know that this output will be the bit stream coming from the radio. One problem is that this bit stream also includes the noise, because the polyphase clock sync has no way of knowing what data is coming from the radio and what data is just noise. So the noise between one transmission and the other. We need some way of synchronizing the packet. As we talked about before, we need to have some sort of sync word to sync the bit stream of the radio. To use a sync word, we can use the block called correlate access code tag stream. This block will look for the access code, which is our sync word, in the bit stream, and it will append a tag to those bits. You will see later what that means. In our case, the IO type is byte, because it takes an input of byte, and the access code is the access code from our radio, which in our case is in X C9 D0 8A 7B. This in binary is the following. Because we need to input the access code in binary. The threshold is how many bits need to be correct in order to synchronize the word. As we said before, there is some leeway in the recognition of the sync word, and we can allow some bits to be wrong and still recognize the sync word. And you can see in the documentation that the threshold is the maximum number of bits that may be wrong. Let's set it to something like 6 bits. So we'll allow 6 bits to be wrong, but still recognize the packet. Let's press apply. And we also need to give the tag a name. Now, tags in GNU Radio are literal tags that are appended to the bit stream, and that can be used later to recognize a particular bit. This block will associate a tag to the starting bit of the packet sequence. With other blocks later, we will be able to read this tag and correlate the first bit of the message. At the same time, this block will actually get also the frame length, and it will store the frame length inside this tag. We need to give this a name. We'll give it the name of length key in order to make it work with later blocks. So this tag name will be appended to the first bit of the message, and it will contain the length of the packet. Let's put it in sequence with the binary slicer. So now the output is the same as the input, with the other difference that there is a tag key in the middle. We need to do one modification, and which is to compact the stream. In this case, the output of the binary slicer is 1 bit. So each sample of the output of the binary slicer is only 1 bit per sample. And the type is actually an integer 8, is a byte, which contains 8 bits. So for each byte in the output, there is only 1 bit. We need to pack these bits into 1 byte. So we need to take 8 output samples of the binary slicer and pack them into 1 byte. To do this, we can use a repack bits block and connect it to the output of the correct access code. And you see that it will take this number of bits per input byte and will output a byte which has this number of bits. In this case, we can leave the settings as default. So the output of this block will be the actual bytes of the message, exactly as we were meant to receive them. We only need to make one minor adjustment, which is to correct the length of the packet. This is because the output of the length from the correct access code is in bits, but we actually want the length to be in bytes. To correct the length, we can use a tag string multiply length tag, change the type to byte, and we can use this to multiply the value of the length key by 1 over 8. This will divide the length by 8. Since this length is in bits and we want the length in byte, by dividing by 8 we'll get the length in byte. So let's add it in series. And now the output will have a length key which is in bytes. And we are basically done, because now we can use a tag stream to PDU to transform these bytes into an output. The tag stream to PDU will take a tag stream which has the length tag name of length key, and it will output a PDU. The PDU is the protocol data unit, which is used by GNU Radio to pass messages. And we can actually use a message debug block, and we can connect the PDU to the print PDU part of the message debug. The message debug is used to print PDUs to screen. There is one problem though. The tag stream multiply length tag shows a length scalar of 0. This is because it is not doing this division properly. We can either say 8.0 to make it understand that this is a float number, or we can type 0.125 directly. Okay, let's try to press play now that the length scalar is correct. We're actually getting an output in bytes. We're getting message debug print PDU verbose, we're getting a length of 28, and the content is written in hexadecimal. You can go to our favorite website to switch between hexadecimal and ASCII. For example, the ASCII to Hex website, and we can convert the string. And we remove the extra content, which is the address. Press convert, and we actually don't get any output. So there is a problem with this string. One main reason could be the endianness of the bits. If the bytes come out to have no meaning, we can try to change the endianness by double-clicking on repack bits and changing the endianness instead of LSB to MSB. This will switch the order of the bits in the byte. This will depend on the Arduino you're using or your system itself. Let's try to run it with the MSB order. And now we get a different output, you see, and this is actually ASCII. So let's copy this and put it into ASCII to X. Let's remove the extra address lines, convert, and you see this is message number 60. We're actually receiving the message from the transmitter. But this is a little bit difficult to use. We need to copy and paste and convert the values. What if we actually wanted to manipulate this data? GNU Radio offers us the possibility to add a custom block. We can look it for as a Python block. With this Python block, we can take any input and do whatever we want with it. We can, for example, put it in the output of our PDU and double-click the properties of the Python block. Here will tell us that we can select the editor to modify the Python code, and it has an example parameter that we can change in the code. Let's open in editor, and let's say that we want to choose an editor. Since we have it, let's use Notepad++ as a program, but you could use also Notepad from Windows. In that case, you would go on Windows. Let's sort it by name. Let's go to System32, and here you will have the notepad.exe that you can use to open up the editor. In our case, we'll use Notepad++, so we'll go on Program Files, scroll down to Notepad++, Notepad++, and press OK. This has opened a new window in Notepad++ with the Python code. We can change this code to treat the signals however we want. We will have a definition of the init, which defines how the block behaves, and then we have a definition of the work, which is what happens to the sample that come in and go out of the block. In our case, we will use an already made code for simplicity, and we'll paste it inside this block. We see here that we've named the block as message handler, and it will register a port which will take a PDU input, and it will define a function to handle the input to the PDU. And this will in turn take the content of the array and print the values on screen. So we are doing what the message debug block was doing, but using our own Python code. Of course, from here we could do anything we want. We could make a GUI to display the data. We could save the data to file and interpret it however we want. Let's see if this block runs by saving it and pressing OK. You see that the name of the block has changed with the name that we defined in the Python code. Let's press play. Let's wait for a message to arrive. And you see, we actually get new message, the length, the content, and the ASCII version of the message. Because this is what was instructed in the Python code. You see that the ASCII was printed using the string function, which takes the input of the byte array and outputs the ASCII string. So now we are getting a good ASCII output. This was all. Now you can play around with the script, and you can try to receive different types of baud rates and change the signals a little bit by modifying the Arduino code.
This concludes the exercise that is included in lecture 7 and 8 of our course. We hope that these videos are helpful in setting up the course for both the teachers and the students. We remind you that the materials can be downloaded for free on the SDR Play website and at the link that you will find in the description of this video. Thank you very much again for your attention, and see you on the next video.